Hello, in today's video we're going to be talking about diffeomorphisms as well as the mean value theorem and a proof of the mean value theorem. So let's start by defining a CK function. It'll be really important when we start actually describing diffeomorphisms. So if I have a real valued function f, we call it CK if all of its partial derivatives of order k are continuous. Now, a function is also CK if it's a function from Rn to Rm, if it is CK on all of its coordinate functions into M. So, in other words, a function is CK if the M coordinate functions are CK. Now, let's define a diffeomorphism explicitly. So if I have an open subset of Rn, and I have a function mapping it to an open subset of Rm, this function is a diffeomorphism if it is C infinity and has an inverse that is also C infinity. Now, what does it mean to be C infinity? Well, a function is C infinity if every single one of its partial derivatives are continuous. Okay, so now let's actually state what the mean value theorem is. So we're going to let f be a function from Rn to Rm, and we're going to have it be C1. That is, all of its first partial derivatives are continuous. Now let x and x prime be 2 points in Rn. Then what happens is the difference of f of x and f of x prime is equal to the sum of the partial derivatives with respect to each coordinate of x double prime times x minus x sub I prime. So, and this is true for some x double prime in the line segment from x to x prime. Now, if we can recall the mean value theorem for one variable, this is something from Calc 1. It says that there exists a point on this line segment from A to B such that f prime of that point is equal to 1 minus b over a times f of b minus f of a. That is the average value of the function on that interval. Okay, so now let's prove this. So we're going to start by defining a function f from Rn to R by t maps to f of t times x plus 1 minus t times x prime. Next, we're going to use the one variable version of the mean value theorem, which we just described. That's the theorem statement from calculus. And we're going to take the derivative of f of this function, so f of tx plus 1 minus tx prime, with respect to t, and we're going to take that at the point t equals t naught. And we're going to see that that is equal to, by using the chain rule, the sum from 1 to n of the partial of f with respect to x sub I, so each coordinate of the point. And then we're going to take that of x double prime. And then because we're using the chain rule, we're going to multiply that by d dt of tx plus 1 minus tx prime. And we see that by evaluating the derivative with respect to t on the inside of that sum, we just get partial f partial x sub I of x double prime times x sub I minus x sub I prime, where x double prime is t naught of x, or t naught times x, plus 1 minus t naught times x prime. And that concludes this proof. So a corollary to this proof is something that we're actually going to use when we start proving things like the inverse function theorem and the implicit function theorem. And the corollary to this is if we have a function from a product space, so Rk cross Rm into R, and that function is also C1, and we have some points x in Rk and y prime in Rm, then f of xy minus f of xy prime is going to be equal to the sum from 1 to m of df dy sub I of x y double prime times y sub I minus y sub I prime, where y double prime lies on the line segment from y to y prime. And the proof of this is fairly simple because we already have proven the theorem. So all we're going to do is we're going to kind of ignore x, and we're just going to apply the mean value theorem that we just proved to the y coordinate only. And that's the end of the proof. Thank you for watching.